Okay, 1-6, function operations and composition of functions. So today we're going to look at operations with functions. So instead of just adding, subtracting, multiplying, dividing numbers, we're going to do it with functions. So just like numeric values can be combined with arithmetic operations, we can do functions the same way. So if we look at this gray box, operations with functions, f and g are two functions with intersecting domains. So for all x values in the intersection, the sum, difference, product, and quotient of f and g are new functions defined as follows. So really, these 4 bullet points are just going to be some notation to look at, and then we'll get into the examples. So the first one, the sum, when we add these together, it's saying you can take function f plus function g, both dependent on x, and this is just a different way of writing it, f of x plus f of g. The difference, f minus g of x, is the same representation as f of x minus g of x, just subtracting those two functions in their like terms. The product, f times g of x, is the same as f of x times g of x. And then the quotient, f divided by g of x, is the same as f of g of x divided by g of x. And here's a little disclaimer, g of x cannot equal 0 because it's in the denominator. Okay, the domain of these new functions consists of the values of x that are common to both f and g. So we are going to talk about domain as we do each one of these. And we have to make sure that the function will still exist with the domain values. Okay, example 1, we are given f of x to be x squared plus 4x. So g of x is the square root of x plus 2, and h of x is 3x minus 5. So we have 3 different functions. We want to find each new function combination and its domain. So we're going to look at the first one. We have f plus g of x. Well, what we're going to do is we're going to take f of x, which is x squared plus 4x, and to that we're going to add g of x, because remember, this is the same as f of x plus g of x. So we can literally write the f of x function plus the g of x function, the square root of x plus 2. So now as we look at combining those, there are absolutely no like terms. So this one is really, really simple. As far as combining, nothing is a like term. So x squared plus 4x plus the square root of x plus 2. So this is our new combined function. This represents f plus g of x. Now we need to talk about the domain. So we do have a square root, so we have to know the domain values that are allowed. X plus 2 has to be greater than or equal to 0, so x has to be greater than or equal to -2. So as it comes to writing our domain value in interval notation, -2 is the smallest value that we can have, and then anything after that up to infinity is acceptable. Okay, so there's the first one. Let's look at letter B. So letter B wants f minus h of x, so we're going to take f of x and subtract h of x. So we have x squared plus 4x, there's f of x, minus. Now, this is where it's tricky. Subtraction can give you some issues with sign if you're not careful. You are subtracting h of x, which is a quantity. So it really is important at this point I put those in parentheses because I am subtracting a 3x and I am subtracting a -5. The next step I'm going to take is to rewrite this without parentheses. So x squared plus 4x minus 3x and minus a -5 is plus 5. Now when I combine my like terms, x squared 4x minus 3x is plus 1x plus 5. So this is my function f minus h of x. And there are no restrictions on these domains. These are polynomials. There's nothing we can't plug in for x. So my domain is from -infinity to infinity. Okay. Next, we're going to look at C, f times h of x. So f of x times h of x. As we write these out, I have x squared plus 4x, and I have 3x minus 5. Okay, so two binomials essentially, so we're going to FOIL. X squared times 3x gives me 3x cubed. The outer, negative 5 times x squared is minus 5x squared. The inner will give me plus 12x squared. And the last will give me minus 20x. So as I combine my like terms, I get 3x cubed. The x squared terms go together, so plus 7x, negative 5 plus 12 is 7, and then minus 20x. And this would be our f times h of x. Final answer there. Okay. Now, again, the domain in this, there are no restrictions on any of the domains from f of x to h of x, and then when we multiply them again, we have no square roots and we have no denominators, so the domain is negative infinity to infinity. Okay, now we're going to look at D, and I'm going to just cut this down a little bit and give myself some more room. I tend to take up a little more than I have space for. Okay. H divided by f of x. So h of x again is 3x minus 5. My f of x was x squared plus 4x. So this is really just putting h of x over f of x. Now if I simplify this, something may cancel. I cannot simplify the top, but the bottom I could factor out an x. Even if I did that though, nothing is going to cancel. So this right here is actually my final answer. This is what I get when I divide those two functions. However, we have a denominator that cannot be 0. So x squared plus 4x cannot equal 0, so we have to figure out what the restriction is, what makes it 0. So to solve this quadratic, I'm actually going to factor out an x. We always want to factor first if we can, and I'm left with x plus 4. So set each factor equal to 0. Oops. X plus 4 equals 0. So I have two restrictions. X cannot equal 0, and x cannot equal negative 4. So as I write my domain, it's going to have different sections to it, 3 different sections. So I can have from negative infinity up to 0. I can have 0 to, up to negative, that's a negative 4, Ms. McDaniel. Negative 4, from negative 4 to 0, and then from 0 to infinity. Okay, and that is our domain, and this was our final answer when we divided those functions. So this is doing some, this is doing operations with those functions, just simply adding them, subtracting them, multiplying, dividing them, combining any like terms just like we would with the numbers. The next thing we're going to look at is composition of functions. This is something that you looked a lot at in Algebra 2. You did start to look at it, I think, in Algebra 1. So it should be a bit of a review. The composition of function f with function g is defined by f of g. Now, I don't like that notation as much as I like the second one, f of g of x. The f of g of x kind of helps me to remember that what's on the inside gets done first, and then I work my way to the outside. So that kind of helps me. I prefer it, but it is important that you know what both of those notations mean. Okay, when the domains of f or g are restricted, this is important. The domain of f of g is restricted to all the x values in the domain of g, whose range values, g of x, are in the domain of f. So essentially, if we have any places that are restricted, they're also in any of the steps, we're going to have restrictions in our domain. Let's look at example 2. We're given f of x equaling x squared plus 1 and g of x equaling x minus 4. So the first example wants us to find f of g of x. I'm going to rewrite this notation, f of g of x So this helps me see that we're going to take g of x and put it into f. So g of x is actually x minus 4. So f of x minus 4 means I'm going to substitute, I'm going to go to f, and wherever I see an x, I'm going to plug in x minus 4. So as I do that, I have x minus 4 squared and then plus 1. And so that's the composition right there, but we are going to simplify this. We're going to FOIL x minus 4. So that would be x squared minus 8x plus 16 plus 1, and that gives us x squared minus 8x plus 17. And that would be our f of g of x. The domain, there are no restrictions on the domain for any of those steps, so from negative infinity to infinity. Oops, what's the bracket doing there? I don't know. Okay. All right, let's look at letter B. G of f of x. Now we're going to go the other way. So I'm going to rewrite the notation, g of f of x. So this helps me to see I'm going to take f of x and I'm going to put it into g wherever I see an x. So f of x is the function, x squared plus 1. So as I look at g, everywhere I see an x, I'm going to put in x squared plus 1. So if it's x minus 4, it's now going to be x squared plus 1 minus 4. And easily simplified, I get x squared minus 3. So that's the composition the other way. And once again, there are no restrictions on this domain, so my domain will just be from negative infinity to infinity. Okay, and then letter C, f of g of 2, I'm going to rewrite it again. So this helps me to remember I'm going to go find g of 2 first. I'm going to get that value. So I'm going to come down here. G of 2 is going to equal 2 minus 4, which is negative 2. So if g of 2 is negative 2, I now want f of negative 2. So I'm going to go to f, which is x squared plus 1, and wherever I have an x, I'm going to replace that with negative 2. So I have negative 2 squared plus 1. That's going to give me 4 plus 1, which is the value 5. So for this one, they just wanted a value, no variables left. Okay. Example 3, we're going to do a little more practice. And in this example, in these couple of examples, we're going to see where we have some restrictions on the domain, and we have to define those restrictions. Okay, example 3, find f of g. So again, f of g of x. Let's start to substitute in. So f of g of x is x squared minus 9. So I'm going to go to f, and wherever I have an x, I'm going to plug in x squared minus 9. So it's going to become 1 over x, which is now x squared minus 9, and then plus 1. And that leaves me with 1 over x squared minus 8. So this gives me my function when I do the composition. Now, if you'll look, in the very beginning, in f, we were not allowed to have negative 1. There's a restriction there. And now at the end, once we've done the composition, we have x squared minus 8 in the denominator. So we need to see what makes it 0 there. So x squared minus 8 equaling 0. It's going to give me x squared equal to 8. And that's going to be, when we're solving a square root, remember we need 2 solutions. So this will give me x is equal to positive and negative 2 root 2. So we actually have 3 restrictions. We have negative 1, and we have 2 root 2 and negative 2 root 2. So instead of interval notation for this one, maybe just to save a little time, the domain, I'm going to write this in set notation. This would be all x's such that x does not equal negative 1 and positive and negative 2 root 2. All right, very good. Okay, letter B. As we look at letter B, the first thing, we didn't say it was the first thing last time, but let's notice it right away here. We have g of x, which is the square root of x minus 3. So right here from the start, we have to set that restriction. X minus 3 has to be greater than or equal to 0. So x has to be greater than or equal to 3. Okay, now let's see what we get when we put that function together, and we'll write the domain at the end. So if I do f of g of x is the square root of x minus 3. So now I'm going to go to f, and I'm going to replace any x's with the square root of x minus 3. So f, let's see, it's going to go right in there. So I'm going to have the square root of x minus 3. How nice is this? Then I'm going to square it, and then minus 2. So that leaves me with x minus 3, undoing that square root, then minus 2, and I get x minus 5 as my final composition. So that right there looks like there are no restrictions whatsoever, and normally there wouldn't be, but this came from the composition of two functions, one of which had a restriction. So that will be a restriction in the very end for us. The domain is going to be from 3 to infinity. Again, coming from the fact that at the beginning, x had to be greater than or equal to 3. Okay, now that probably seemed familiar to you. Maybe you're a little rusty, but it should be pretty familiar. Now we're going to do something that's not so familiar. We're actually going to go in the reverse order with these. So looking ahead, one of the concepts you're going to explore in calculus is decomposing functions, so breaking them down into two simpler functions. We're going to work backwards from what we just did. So in example 4, we want to find two functions. Now we want to get f and g, such that h of x is the result of f of g of x. So what we have is a composition, and we need to break it down into two smaller functions that this composition came from. Neither function may be the identity function f of x equaling x. That's kind of cheating. That's just making it a little too easy. So if we look at the first one, h of x, we want to know what f of x and g of x did this come from. So as you start to look at this, I'm going to be honest with you, there are several different ways to write this. There is not just one right answer. As long as you break things down correctly, when you put them back, if you get the square root of x cubed minus 4, you're fine. So we're going to take a look at one way to do this. I am going to look at the inside under that radical. That's the first thing I see, and it looks to me, the way that I see it, is maybe an x cubed minus 4 was put in for an x, the square root of x. So I am going to write mine this way. I'm going to say that g of x was the x cubed minus 4. And I input that because, again, I want f of g of x. I'm taking g of x and putting it into f of x and getting this h of x as a result. So I'm going to make f of x the square root of x. So now the composition would work. I would take g of x, x cubed minus 4, put it in for x, and I would have my h of x. Okay, letter B, same type of thing. If I were you, I'd pause this video, try to figure this out, and see what you get. Again, there are different answers. Okay, the way that I looked at this is I saw a greatest common factor. Again, we want f of g of x. I want the f of x, and I want the g of x. G of x has to be put into f of x and get that h of x as a result. So I see a greatest common factor of 2, and that leaves me with x squared plus, oh, actually, I'm sorry, this is a typo, guys. There was supposed to be, let me fix this right now. This is supposed to be 20, and then it works better. That is supposed to be a 2x squared plus 20x plus 50. That's a little nicer. So when I factor out a 2, I would have x squared plus 10x plus half of that is 25. This is a perfect trinomial square, so I would have 2 times the quantity, x plus 5, all squared. So this is my h of x, what I really have. And again, there's not just one right answer. This one, to me, what I see is an x plus 5 was maybe plugged into a 2x squared. So I am going to set g of x equal to x plus 5, and my f of x I'm going to say was 2x squared. Okay, that's just one way to do it, but that's the idea, is taking a function and breaking it down into 2 simpler ones. Okay, the last example we have is an application, and I think this one's pretty interesting. It's something a little different. Okay, so let's look at this. Computer animation. To animate the approach of an opponent directly in front of a player, a computer game animator starts with an image of a 20 pixel by 60 pixel rectangle. Now I'm going to draw that right now. 20 pixels by 60 pixels. And gosh, that looks pretty square, Miss McDaniel. Let's draw something a little more. 20 pixel by 60 pixel. Okay. All right, that's better. The animator then increases each dimension of the rectangle by 15 pixels per second. So it starts out as a 20 by 60, but then to that we would add 15 pixels per second, so plus 15t. And t is going to equal my seconds. Okay, just to be clear on that. Okay, so letter A. So there's what's going on. Letter A, what do they want us to do with this? Find functions L of t and A of L, where L is the length of the rectangle with respect to time. The length of the rectangle with respect to time. So it really doesn't matter which one you use. And A is the area with respect to length to model the data. Okay, so the length dependent on time. You can pick either one you want. I'm going to pick 20, even though it might look like the length is 60. You could use 60 plus 15t, either one. 20 plus 15t. This represents the length of one of the sides based on time. Okay, the other one they want is area based on length. Okay, now the first thing we know that area is length times width. So as we look at this, I'm going to take that off of there now. So length times width. When we started out with 20 by 60, they are different by 40. So one length of 20, and then you have another length of 60. So if you have length, the other length is that length plus 40. And that's going to stay constant even as time goes on because they're going to increase at the same rate. So there will always be 40 as a difference between the length and the width. So length times width gives us area. And when we're basing it on just the length, that is how they differed originally by 40. Okay. All right, so there's what we have as far as functions. So letter B says to find A of L. And what does that function represent? Well, so if I want A of L, well, L is based on T. So let's see what we get when we do that. So if we do A of L of T is really 20 plus 15t. So I'm going to take that and I'm going to substitute that into my length. But you know what, first, nope, that's okay. I'm going to leave it just like that. I was going to maybe go distribute that L, but we can leave it just like that. So now I'm going to go to A, my function for area, and everywhere I see an L, I'm going to plug in 20 plus 15t. So I've got 20 plus 15t times 20 plus 15t plus 40. So that's going to give me 20 plus 15t and 60 plus 15t. So we can see what that gives us. It's basically, now I'm gonna FOIL this out for us here in a second, but that basically is giving us area based on time, using length, but how the overall area changes based on time. Okay, now as I FOIL this out, I'm gonna get 1200 for the first. Outer gives me 900t. The inner gives me 300t. And the last gives me 225t squared. So as I combine those, I get 225t squared plus 1200t plus 1200. So this is a quadratic where we have, actually I'll put it down here, area over time and how that changes. Okay, and then the last, let me highlight that, that was our final answer there. Okay, and the last says, so how long, so they're looking for t. How long does it take for the rectangle to triple its original size? Well, triple means times 3. So the original size was a 20 by 60. So the original area was 1200. Okay, so if I want to triple that, 1200 times 3, I want to know how long it will take to get to 3600. So I'm going to set the area equal to 3600, 225t squared, plus 1200t, plus 1200. It's a quadratic, so I want to set it equal to 0. I'm going to subtract my 3600. And 0 is equal to 225t squared plus 1200t minus 2400. Okay, we have a greatest common factor of 25 here, so I'm going to factor out a 25 and let my numbers be a little bit smaller. 9t squared plus 48t plus 96. So if I go to put that into my calculator, I'm going to actually get t equaling 1.55 seconds. So as you graph this, just a quick sketch, you should get something like this. So that's going to be my 1.55 seconds. So that's how many seconds it would take for it to triple in size. Okay, and that's it for 1/6.